Thanks so much for having me. I'll switch over to my slides here in a second, but I just wanted to mention briefly that if you have questions, I can take them as I go. Don't think you'll be interrupting. I want to make sure everybody understands the content before we move on to the following slide. So with that, let me know if you can see my slides.
Yeah, I can see it perfectly. Yeah, it looks like
Can
it's
you see
showing.
the presentation view or my view?
Yeah, I'm seeing your view. I'm not seeing the presenter's view.
Okay.
Let's see.
Is this better?
There it is. Perfect.
Okay, excellent. All right, so let's just dive right in. I'll start by describing a little bit of what the traditional DoD test process looks like, because I'm not sure everybody's familiar, but legally the Department of Defense, and when I say T&E, I mean test and evaluation, we'll go into exactly what that is. But legally, according to Title 10, there are two pieces to the way that the DoD independently verifies and validates the systems that they buy. The first step in that is usually a developmental test. So this is something that usually is performed by contractor and supervised by the government. And this is done while the system is still in product development. We do this to certify that it's meeting certain technical metrics, that it's maturing properly. We often do this in prototypes and using simulations. And then finally, when the system is all but ready to go, we try to test it in what we call an operational test. So we have a finished representation of the system, and we try to test it under realistic combat conditions, including a realistic representation of the adversary, if that's available. And usually what we focus on here is not so much the technical metrics, but operational metrics, right? Does it contribute to mission success? Is it effective? Is it suitable? And is it survivable? So that's the traditional process. It sounds very linear, and it is. And that's because it was written and really thought through and legalized when we were largely focused on hardware systems. And so traditionally, when we evaluate hardware systems, we focus on rigorous experimental design, right? So we actually figure out what are all of the things that I want to test. What are all of the metrics that I want to take? We usually focus very heavily on only quantitative metrics. And we figure out what factors affect the system performance, right? If I'm testing a tank, I might want to test it in different weather, on different terrain, with different targets, et cetera, et cetera. And we usually will combine those factors and design a well thought through experiment and focus on what we call statistical measures of merit. We focus on power of the test. Another way, the other way of describing that is if something is wrong with the system, what are the chances I'm going to find it? We focus on things like designing the right sample size. How many times can I test the system before I get the desired level of confidence that it works or it doesn't work? And of course, each sample costs money, so there's an obvious tension there. And we write up our test plans and conclusions. So my point is that it's a very well-established process, but it's a process that's well-established for hardware systems. And so when we run into AI-enabled systems, we inevitably run into some challenges with that process. For one, tasks are much more dynamic and poorly constrained, right? So in an AI-enabled system, we often don't have the best idea of what it's going to do or how it's going to behave or how it might change the workflow that we've introduced it into. And so our successes are much harder to measure. I'm not just talking about measuring like a circular error probable or, you know, a speed of advance or something like that. Now it becomes something much more complex. At the same time, failures in AI systems often can be catastrophic. And so here we are in a situation where I don't even know exactly what I want to measure necessarily or how the system might fail. Another problem is that because we don't understand AI systems as well as we understand hardware systems, I don't know what those factors are that I need to vary. I don't have a terrain necessarily. I can hypothesize that my AI system will work differently in a forest environment than in an urban environment, and it probably will. But I don't have a clear enumeration of all of those factors the way that I do with my hardware systems. So then generalizing any kind of result is difficult. And so where we are really in the Department of Defense as a result of these pretty major challenges is that we're rewriting the entire process of test and evaluation. We're having to upgrade our workforce, our systems, our methods, everything that's there. And so you'll see a little bit of that in this talk today. So when it comes to AI-enabled systems, we talk about a concept called AI assurance, right? And the idea behind it is that this is a new technology. It's very exciting and it has tremendous potential, but it is hard to understand and sometimes even hard to predict. And so in order for us to actually deploy it, in order for decision makers to base their decisions on this technology, we have to show whether it's trustworthy or not. And so we think of AI assurance as this concept that kind of safely helps us unlock the potential of this technology. You'll see a reference there at the bottom. I highly recommend you look that up in your spare time. It's the UK government's AI assurance, what they're calling a biscuit book. So it's meant to be enjoyed with tea and biscuits, which means that it's very easy to digest. It's really not like a long mathematical text. It's actually very kind of pleasant to read and easy to understand. So I recommend you look that up. It talks about this concept in a little bit more detail. And one thing you'll see me stay away from is the word trust, except for when other people use it. And the reason we recommend staying away from the word trust is it's a very hard to define concept. In fact, if you try to look up its definition, you'll see that over 300 definitions are available. And most of them are not quantitative, right? So again, when we try to actually evaluate these systems, that's not a desirable property, something that's badly defined and is not quantitative. Also, people talk about building trust, which has an implicit kind of connotation that trust can be blind, right? And people do blindly trust systems. That's very undesirable in highly consequential DoD systems. So trust is a bad word in our community, but we do use the word trustworthy, right? And a colleague of mine did a really good job defining trustworthiness, and he defined it based on 3 basic principles. So the system is trustworthy if, when used correctly, it does what it's supposed to do. When used correctly, it doesn't do what it's not supposed to do. And then the third pillar that's really important is that you've trained your humans to use it correctly. Right. So when we talk about, you've tested a system in every which way, what happens after that? Well, what happens after that is you now have the responsibility to transfer that knowledge to the operator, to the commanding officer, to the acquisition official, so that people figure out how trustworthy the system is and where it's useful, where it performs, and where it doesn't. I'm going to quickly, thank you. I'm checking the chat to see that there are no questions, but instead references, which is wonderful. Thank you very much. So now we've established what trustworthiness means, and I recommend reading David's paper on that. It has a nice discussion of all of these concepts. How does trustworthiness relate to AI assurance, the concept that we're here to discuss today? Well, AI assurance is really a collection of arguments. Some of them are based on evidence, and some of them are based just on logic that show that the system is sufficiently trustworthy for its expected use. And so when we write our assurance cases, usually what we focus on is whose trust is needed. And so in an AI system, it's certainly the warfighter for the Department of Defense, but there are a lot of other stakeholders as well. You have your commanding officer that makes a decision about how we're going to fight this fight. You have an acquisition official who wants to make sure American taxpayer dollars are well spent. You have the American taxpayer who wants to make sure you're not building Skynet. You have an international ally that wants to make sure your systems are interoperable, for instance, right? So there's a lot of different stakeholders, and all of them have these different requirements. So we want to write those down. Then we try to assess how confident does each stakeholder have to be in those claims. Does somebody need to be 100% confident? Well, maybe with like a AI-enabled nuclear launcher, somebody might want to be 99.999% confident, but with a chatbot, maybe not. Maybe 80% is good enough. And then once you figure out what claims do I have to support with what level of confidence, then you figure out how do I get the right evidence to justify that confidence. And so once you have that structure, that's called an AI assurance argument. And so we're able to build those cases and write those arguments with supporting evidence. So really all this is to say, wait, then who our stakeholders are, what we need to show, and figure out how to show it, and then execute and see whether we can show it or not. Some of the ways that we measure AI-enabled systems are still very traditional, right? We still talk about test and evaluation. In this case, when I talk about a test, I mean a singular event, right? So I fire and I figure out whether I hit my target, something like that. Very simple function. When I run multiple tests, I combine them into an evaluation and provide an overall judgment. And then we also talk about V&V, verification and validation. And those are the two things that we've got to always care about, and anybody who's building anything usually cares about. Verification is, did we build the thing right? So if I give it 2 + 2, will it give me 4, right? And validation is, did we build the right thing? Did the operator need a coffee maker or a calculator, right? So pretty basic questions, remarkably difficult to answer at times. The way that test and evaluation, traditional kind of test and evaluation factors in AI assurance, there's a lot of overlap. And test and evaluation tends to produce a lot of the evidence that we need to build our assurance arguments. And some of it, again, is going to be very familiar to a lot of testers, like testing, whether we're complying with design specifications, can it fly in different weather at such and such altitudes and things like that. Reliability testing, mean time between failures, right? How long until the engine fails? Interoperability testing, does this part of the system interoperate with all of the other parts of the system with which it's meant to interoperate? And of course, evaluating it with humans. But there are some additional innovative techniques that are introduced by this new technology as well. We're much more focused on digital twins and virtual test beds and modeling and simulation, right? If you think about, for instance, what it might take for me to test a drone out on a test range, the amount of safety assurance that I have to establish before anybody will ever let me on a range is tremendous, right? And so for that, you will see me using a lot of virtual test beds, digital twins, M&S, et cetera. They're also formal models, right? I mean, in the end of the day, these are mathematical models. And even though they're hard for humans to understand because they get incredibly complex, some of it is about just mathematical proofs and formal methods. And so in some cases, we can do that. And then another kind of interesting aspect to AI-enabled systems is that we're introducing a whole new attack dimension, right? So with traditional systems, we've worried about cyber for a long time. But now we have adversarial AI. I'm sure many of you have seen fun examples of turning stop signs into speed signs online, or turning pandas into gibbons. You take this to a nuclear-powered AI launcher, an AI-powered nuclear launcher, and you start really worrying about what people can do. And in practice, of course, it's really hard to get to that level of an adversarial attack, but some attacks are pretty easy, and our systems are actually remarkably brittle because we tend to use open source software to build them. So a lot of this test and evaluation of it that is kind of traditional and a little bit innovative is very much intertwined into AI assurance, but does not comprise all of it. Importantly, and I like to really stress this in all my classes, test and evaluation informs system development, informs characterizing the capabilities, and informs decision makers. Test and evaluation is not an area, is not a place, and is not a set of people that decides whether or not the system gets fielded. Testers tend to look like me. They tend to be statisticians. They're not operators. We try to involve operators as much as we can in tests to make them operationally relevant and realistic. But in the end of the day, the job of a tester or an AI assurance colleague is to create that risk space so that somebody else can make a decision. And we very much recognize the fact that the decision changes depending on the operation. right? So even for the same exact system, today, 80% good, whatever that means, might be good enough, and tomorrow it might not be if the operation is different. And so we leave that decision to somebody in uniform, but our job is to inform them to make that decision.
And Jane, we did have a question coming in from our audience, and we're very thankful that folks are coming up on the net. And if I'm phrasing the question correctly, I want to make sure that I'm capturing it. But in the test and evaluation space, there is a number of things that I know you folks have to really account for when it comes to legal compliance and the other types of things that are associated with ensuring that it follows maybe the law of armed conflict in practice and in concept. What types of systems or what kinds of use cases have you seen in your experience that would be instructive in that space?
So, I would say that up until AI-enabled systems, that's a great question. Up until the introduction of AI-enabled systems, I think that compliance, for the most part, came from our expectations of the humans that are handling the system. Right. So if the system is not making any decisions, if the system is not intelligent in any way, then primarily we have relied on humans to know the law and also on the process, right? So before anybody fires anything, right, there's usually a conversation with a lawyer that occurs, et cetera, et cetera. It's only with AI-enabled systems that it starts getting a little bit more interesting as we potentially look at taking some of that context away from the humans or potentially delegating some decisions eventually. So I have not seen many use cases of that because it is all very new. I will say that especially when it comes to lethal autonomous weapon systems, this is incredibly well thought through in the 3000.09 directive. So that's the directive that was originally written in 2012 and then reissued in 2023. I really recommend you read this on having to do with the development and fielding of any system that is semi-autonomous or autonomous and has a lethal capability. So a really important directive to know about it. It is well written and again, kind of easy to digest, I think. And so that's where those things start coming a little bit more. And then the other place where you see it appear is actually, this leads me perfectly to my next slide, which is the DoD ethical AI principles. And that's the only place where I've seen, giving thought beyond the traditional people and process that exist that have been largely sufficient up until that point. So when you look at CDAO and their AI assurance framework, which is kind of the main framework right now for the DoD, and it really has two parts. One is this test and evaluation piece, and the other one is the responsible AI principles. And so our DoD was the first to adopt ethical AI principles. I think just over 3 years ago at this point. Multiple militaries have followed, but we were the first, and most of the ones that have followed mirror ours pretty closely, with some interesting deviations here and there, but nothing life-changing, I would say. And so you see those 5 principles depicted around the circle here. And so the first principle is responsible. That places really the onus on the human using the system, and they're meant to exercise the system responsibly, use appropriate judgments and care. Right, and so there you see a tie to kind of law of armed conflict. And by the way, these principles were written largely based on those types of documents. Again, the principle responsible implies that you've communicated to the human the limitations of the system, right? So it implies that good testing has taken place and that we've found intelligent ways to communicate the system's shortcomings and its advantages to the human responsible for executing. Then there's equitability. Equitability is exactly what it sounds like. It's about unintended bias. And the word unintended is very intentional here because if I want a system that's going to operate in the desert, I'm going to bias it to operate well in the desert and nowhere else, and that's okay. Once you get into systems that are making decisions, for instance, about personnel, then you get into all kinds of traps with unintended bias, and you have to be very careful. And that's largely what this principle is about. Traceable. I want to highlight traceable. It's a very good word that I kind of juxtapose against transparent. for instance. So we don't expect full transparency into how these systems work because they are entirely too complex for most humans to understand. But we do expect traceability. We do expect to know what data was it trained on. We do expect to know how errors propagate throughout the system. And we do expect the right humans to have access to that kind of information when they need it. That's traceability. Reliability has to do with the fact that you've tested the system and it's reliable kind of in the common sense, so you can rely on it to accomplish your objectives. And then governability has to do with unintended consequences and unintended harms. And it basically specifies that you have to build in guardrails, if you want to call it an off switch, something along those lines, where if a system starts going off the rails, we have an operator who's able to turn it off and accomplish mission anyway. That's the simplification kind of that principle. So those are probably your closest tie to that question. Again, the document is out, or a couple of documents out, one on the definition of these principles, another on the 6 tenets across which they will be applied. And then finally, there's the responsible AI strategy and strategy pathway that's out as well as of last year, that talks about assigning no kidding responsibility to different components of the DoD for executing these principles. Inside this framework, what you see is the 4 pillars of AI test and evaluation. So the first one, now we're talking about the rectangles, is model integrity, right? So if a contractor, if and when a contractor submits the model to the government, which usually is what happens, we don't usually develop our own, the government has a responsibility to independently test the model, usually on a withheld test data set. Then we have system integration, right? So you have a model, now you have to build it into the system within which it will operate. But all kinds of fun things that go wrong at this step, because we usually take our new shiny model and bolt it onto a legacy platform that was never meant to interact with AI. So all kinds of compatibility issues, mostly things overheating. That's what I've seen in my experience. And then human factors, of course. So people mistakenly think that if we take some human decisions and delegate them to a machine, the human factors are less important. They actually become more important because now a human has less context and fewer touch points with the system. So it's more important to make sure that those touch points are very meaningful. And then we still very much focus on operational performance, right? It's paramount to test your system in an operationally realistic environment and against a realistic adversary. So what I want to do next is get into these 4 rectangles, and we will especially dive into model integrity, because I would like for you to walk away with a little bit more of an appreciation of what it actually takes to test one of these models, let alone a system. So you'll see on the top right, just so you don't get lost, you'll see on the top right where we are in that circle and in the rectangle. So right now we're in the model integrity piece. And when we focus on model testing, we usually focus on 4 pieces of it. The first is integrity. So literally, my contractor has trained a model on some set of data. And what I want to do is test it independently on a different set of data that the contractor has never seen, right? To kind of assess, how good is it in a lab setting in the best possible condition. We also here usually look at competency. Competency is the idea that, well, you've trained a model on a data set. Once you finish training, any data point the model encounters after that is a new data point for it, right? It was not trained on it kind of by definition. So how competent is that model to be acting on that data point? In other words, if I trained it in the desert, for instance, and now I'm operating, and then it snowed, how competent is that model to make a decision in the snow? Robustness has to do with the way that I've defined it, and not everybody defines it that way. How does a model perform under natural perturbations, right? So if you're flying a drone and it's especially sunny or especially cloudy that day, how does that affect performance? So you identify those edge cases that tend to occur naturally, but are unusual enough to trigger different performance potentially. And then we look at resiliency. How is the model able to adapt or recover from when an adversarial attack occurs? So now what I want to do is dive even deeper into this topic, but just the integrity piece. So we're within model testing, and we're going to go into integrity. And what I want to do is just give you an example of how we've actually done it to just give you some familiarity with what it might look like. So what you see here is a single frame of drone footage. This was actually from Project Maven. So this is from a real project that many years ago. So it's kind of out in the open at this point. And what you see there is a bunch of objects in the frame that we would care about. In particular, in blue, you see motorbikes, you see vehicles, and in green, you see people. And what you see there is ground truth, right? So a human went in and labeled this. They drew bounding boxes around vehicles and people. And to me as a tester, what I care about is actually just this. I really don't care about what's happening in the rest of the image. I care about where my ground truth is. So to simplify, this is what, as a tester, what my ground truth would look like. To clarify, that frame that you just saw is part of a video stream, right? A full motion video stream. And what I would usually see is 30 of these frames per second. So we're going to take these measurements many, many, many times, but I'm going to show you what happens just in one of those frames. So as a tester, I have my set of perfectly labeled data that I've reserved that my vendor or my contractor has never seen. And I care about where those boxes are. Now, the vendor is going to submit a model. I'm going to call it the black box because I really have no idea what's happening inside that model, usually for IP reasons. And I'm going to put this image without the boxes through that model. And it's going to make some observations about where the model thinks vehicles and people are, or any objects of interest. So these boxes, these red boxes here, at first, they're called inferences, right? So model provides inference. It says, hey, I think there's an object of interest here, 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 and there. Now, that inference usually comes with a box, a label, right? I think this is a person, or I think this is a vehicle, or something along those lines. And usually a score. And that score says, how confident does a model think it is that something is really there? So if a model is only 20% confident, like, hey, I think there's something here, I think it's a person, about 20% sure, I may not want to bother with that, right? Because that's a lot of false detections if it's not very confident. So I usually will set a threshold to say, hey, if it's not above 60 or 70%, please don't tell me. So if a model produces an inference, right, a box, a label, and a score that exceeds that threshold, that's greater than 60 or 70%, something along those lines, then I'm going to call that a detection. And so what it will look like to me as a tester, it would look like this, right? So here I have my blue and my green frames that are the ground truth, and then the red frames, which is what the model thinks it detected. And now my job as a tester is to compare this. I'm going to show you how I compare these two in this frame, but again, keep in mind, I'm actually doing this for 30 frames per second, and I'm doing this for hours of video. So again, the first thing I'm going to do is remove the background because it just confuses everything. And then the next thing I'm going to do is look at these red boxes, the model detections, versus my blue and green boxes. Can you see my cursor when I show it that way?
Absolutely, yes.
Okay, good. Very good. That's actually helpful in this case. So let's look at this guy in the top left corner. What you see there is a red box without any blue or green boxes nearby, right? So that's a detection by the model, but I would call this a false positive, right? So the model thinks there's something there, and there's clearly nothing. If you look at this blue box in the middle that has nothing red associated with it, that's a false negative, right? So there was something there, and my model totally missed it. And then we have everything in between. We have this guy here, that's a red box, pretty much on top of the blue box. That's clearly a really good detection. And then we have some things here, like what about this? It's kind of near the box that it's supposed to be near, but there's zero overlap, right? So I'd probably call that a false negative as well. Well, actually, it's both a false negative and a false positive, right? Because it didn't notice this, but it noticed that. And then you have things like this, where there's overlap between the truth and the detection, but it's highly imperfect, right? And so how do you count those things? So there's a lot of decisions kind of that happen here. And the one number that you'll probably hear about is a number called IOU, intersection over union. And basically what we do is we calculate intersection over union whenever we have two overlapping boxes. So intersection is this area here where the boxes overlap, and the union is the total area of those two boxes. And so for each of these sets of overlap, we'll calculate the IOU, and we set a threshold and we say, hey, if the IOU is high enough, if their overlap is high enough, then I'm going to count it as a correct detection. And if it's not, then I won't. But there are some interesting considerations that come with this, like how big of an IOU do you really need, right? And so here you see pictures of some, IOU thresholds. For me, it's always been very surprising that a 25% IOU looks this good. I would think that it would look a lot worse. And then, of course, a near perfect IOU maybe looks something like that. So, when would you choose which one? Well, you almost never want to choose something this perfect, because then all of your models will just look terrible. And if that's really, the right answer for your use case, then okay. But in most cases, it isn't. Do you really need this kind of perfect localization? Usually you don't. If you're trying to alert the user that, something's in the picture and the user might use this for targeting or something, so you care about localization, something like this is usually good enough. If you're just trying to alert a user that, hey, that truck that you've been looking for is suddenly in the picture, well, they might not care about perfect localization at all. They just care that it's anywhere in the frame. So a 25% IOU is perfectly acceptable. So there's really no kind of hard and fast rule. It really depends on your operation and what you're trying to do. Usually we set the IOU, between 50 and 75%, but I've absolutely seen cases like the one that I mentioned, that if you're just looking, for a specific vehicle, or for instance, in Project Maven, one of the things that we really deeply cared about was whether there is a child in the scene or not, right? Because all kinetic action would stop if there's a child in the scene. I don't need to know very precisely where the child is, right? So I might be okay with this IOU here, just alert me if there's any chance of a child in the scene, and then we'll have the human verify. So that's kind of what you see here, just some of the qualitative decisions that we're making. And so based on that, we will decide which of these overlapping boxes we're going to count as detections and which we aren't, right? So this is clearly a false positive. This is clearly a false negative. There's a false positive and a false negative here. And then we're going to decide, like, this one, is near perfect. This one is probably a miss, et cetera, et cetera. And again, what we're going to do is collect these numbers for each frame, and there are millions of these frames and hours of video. And so what we'll do is we'll calculate some numbers based on those true positives and negatives. We're going to count them, and we're going to calculate things like precision, so proportion of the detections that are correct. Of all the things that you told me were tanks, how many were actually tanks? We're going to calculate recall, proportion of objects correctly detected. Of all the tanks that were there in the frame, how many did you pick up? And then we can calculate fancy averages of these numbers, like the F1 score, and then look at them in a variety of conditions, right? Like, what do precision and recall look like for big objects and small objects? What do they look like depending on the sun angle? What do they look like depending on the terrain, et cetera? And we will just analyze this ad nauseum for, millions of frames, and come up with some overarching metrics for our military leadership that says, hey, here's how good this model is just at this task, right? So if you recall, we're just within model integrity rectangle, right? Just focused on that one line. And this is just one piece of that one line. So this is one of the metrics that's the easiest for us to calculate. We do this fairly well, and we know how to do this. That's why I'm focusing on it, but it's just one tiny part of what a test and evaluation strategy looks like. In that same project, in Project Maven, we discovered that one of the other things, for instance, that the users cared about was not just single frames, right, but actually tracking an object through many frames. And so it turns out there are a variety of tracking measures there as well. There are false positive and false negative tracks, just like you see here. So this is a track here that would be a false positive track. There's no big circles, no ground truth around it. These will be misses, right? So these are big circles. There's no machine track associated with it. But then there are other fun things, right? Like you can calculate the distance between all of the points of the real track and the machine track. You can also calculate, different ratios of all these things, and then things mismatch, right? If you have two cars going through an intersection, it's very common for a model to get confused for a bit about which car is which. We need to take those things into account. We care about things like track latency. How long does it take to establish a track? And then we care about things like track continuity. How many times does a track get interrupted? In other words, if you're tracking a person or a vehicle, and now an analyst spent some time enriching that track with information, oh, I think this is terrorist Joe, and then that track disappears because Joe goes behind a tree. Now he reappears, maybe the model picks him up again, but it picks him up as a new track, right? So all that work enriching that track is lost. So we really care about things like track continuity as well. And so with each of these use cases that you think of, there are all of these countless metrics that we can come up with. And the trouble really is aggregating all of those metrics into no kidding decision criteria. Oh, does this mean this model is good enough to deploy or not? So that was just one part of this model of how we measure model integrity. Let's say you have a model that you're reasonably comfortable with. Again, the next thing that we tend to do is usually bolt it onto a legacy platform. And then we care about functionality and integration. And so things that we tend to measure at that stage are, do things actually turn on? Does the system perform correctly? Is it compatible in terms of data flows and data formats and data speeds? And is the whole system secure? So there are all kinds of interesting things that can go wrong during system integration. In my experience, again, the most common problem was actually things overheating and melting because of the unexpected heat associated with all the compute that we bring in, associated with all of the AI, obviously, that we're trying to do. The next step, you've integrated it onto a system, is integrating the human. And what the CDAO has done is they've issued this really robust human system integration framework. It's more than what you see here on the slide, but this is a good introduction. And they've tied their human system integration framework to the OODA loop, which I think is very useful. It just makes things a little bit more clear. Now, it's also very well tied to the responsible AI principles. So again, that brings us back to that really good question that was asked earlier. So if you think about, the observe and orient pieces of the OODA loop, what are some of the things that we might care about that we know how to measure really well? Situational awareness, right? Is the information coming in the right way, at the right time, in the way that a human can understand? Is the information accurate and timely? All of this, fits into very traditional SA and information quality types of metrics. It also very much correlates to the responsible AI principle, right? You need to understand what's going on in order to use the system responsibly. If you look at the decide piece, this is where the reliance piece comes in. Will the human adequately rely on the system when it's good for what they're trying to use it for? Things like emergent behavior, both by the system and also by the human. Like if the system is actually helping the human save time, what else does the human do with that time now, right? What are some of those decisions? We want to calibrate workload. If the human is sitting there trying to catch AI errors because the system, maybe is producing too many false positives or something along those lines, then the human is likely overloaded and probably shedding other tasks. So workload is something we want to carefully calibrate. We also don't want to underload the human so much that they're falling asleep at their desk. And then, of course, the act piece. Is the system actually usable? Can you use it to accomplish what you need to accomplish? No more, no less. A lot of that has to do with the governability principle. Have we allocated all the functions correctly between the human and the machine? So all of this ties very nicely to the responsible AI principles and to kind of how warfighters do business. And then we get into operational test. And with operational tests, again, the goal is to measure these three quantities: effectiveness, like does it actually help you accomplish mission? Suitability, is it suitable for operations? Is it interoperable? Is it reliable? Can you maintain it from a logistical perspective? And survivability in the physical sense, in the cyber sense, and also in the adversarial AI sense. What are the different failure modes in all of these opportunities, and how do you quantify or avoid some of those risks? AI systems are very complex, so quantifying all those risks is not always an option. And so instead, what we're really aiming for is designing systems that fail gracefully. I will skip this to make sure we get to our example here. I want to really stress the importance of operational testing, because operational testing is really where we see whether the system contributes to mission. That's more important than any technical metric. And this was a really great example. This is one of my first projects at the Joint AI Center, where we really saw the distinction between a technical metric and an operational metric. So this is a humanitarian assistance and disaster relief mission, a HATTR mission, that was meant for wildfire detection. So with the basic idea being that when there is a wildfire, the way that things were done at that time was you had two humans in an airplane circling the area, one human taking notes about where the fire was, then they would come to the ground, draw it on a map, and then send in the firefighters. That entire process took hours. And so in that time, not only is the damage done by the fire, but also the fire moves and you're possibly putting people in danger. And so the idea that they had was, what if we had an MQ-9 circling the area using AI to detect fire perimeter and sending that information down instantaneously? And so we did that. And what you see here is the field of view of the MQ-9 and the fire perimeter that it's outlining as it's circling. And what you see in the video, I hope, is this big fire perimeter, and then also these tiny points that keep popping up that are going to be important for some of our analysis. As we analyze these data, what we saw was 25 times more false positives than true positives, right? So to me as a statistician, as a metric, this is terrible performance, right? This is awful. However, when you look at this with an operator, when you focus on the operational metric of does this actually help mission, and you look at this, what you see is, yeah, you do get lots of these little false positives, but you also very clearly see the big fire perimeter, right? So those false positives really don't distract from your mission whatsoever. So this is one of those things where our technical requirement was not met, but our operational requirement was met very well, actually. It was a highly effective system, obviously worth fielding, right? So again, if you look at the false positive counts versus true positive counts, not looking at anything else, you would never let that system out in the wild. But when you looked at the area, the true positive area, right, was enormous. That's the area of the actual fire. And then you had, yes, you had some false positives that were maybe a little bit distracting, not distracting enough to actually foil the mission. So one kind of last thought that I want to leave you with is something that the department has not spent enough time thinking about, in my opinion, which is, okay, so you've assured the system and somebody has decided that it's worth fielding. Now what? Right now you deploy the system, and we're used traditionally that we deploy, right? I test the tank, I conclude the tank's good enough, I deploy the tank, I don't worry about the tank anymore. Well, guess what? With these systems, runtime assurance and performance and reliability during the actual operation is actually really important. And so there is no standardized approach right now, but we have some general guidelines for what we call runtime assurance, right? Once the system is out in the wild, who's measuring its performance, and how are you potentially augmenting it? So the first step, of course, is defining performance metrics, right? So what are some key performance indicators that reflect your desired system behavior and functionality of the system? This should be aligned, again, with the system's objectives, right? Let's not focus too much on the technical metrics. Let's focus on operational metrics. Then we establish benchmarks, right? What is a set of benchmarks that are acceptable levels of performance? That's going to vary drastically by operation by the system, but they can, in many cases, be derived from historical data, from industry standards, sometimes from expert opinions, etc. And they should serve kind of at least as a reference point. And then we're going to monitor the system. And this really requires a lot of mechanisms and implementation, right? You need to log data during runtime. You need to track performance metric. You need to, in some cases, conduct real-time analysis. You need to actively monitor the system so you can identify if any deviations exist from expected behavior. And then what happens if there is an error? What is your error handling mechanism? Do you have a fail-safe mechanism or a fallback mechanism? How do you incorporate error detection? And then how do you correct the errors? And what are your alternative actions? There's a lot of emphasis that we place on feedback loops with the user, right? So you need to make sure that your stakeholders are able to provide their observations and experiences with the systems. These are still way too new to just kind of feed them and forget about them. And stakeholders are really our best chance at identifying areas for improvement. And then how do you keep providing the validation and verification? Do you continue running test scenarios? Do you continue testing in a simulated environment? Do you conduct controlled experiments? And finally, iterative improvement. So based on the insights that you're getting from monitoring, from users, from validation, what is your actual pipeline for iterating on the system? How are you going to use that data to identify patterns, to diagnose issues, to implement any necessary enhancements or optimizations? So runtime assurance is very much an ongoing process and requires a lot of continuous effort to maintain, to improve performance and reliability of the system. And currently, I would say we're probably not placing enough emphasis on it. So it's something we're thinking through more in the research community. I'll stop here and leave some time for questions or discussion.
Well, thank you very much, Jane. That was wonderful. And we do actually have another question from Mark Meyer. And we appreciate that. And I'll also probably ask for your thoughts on the article that you were quoted in from Frank Bajak this weekend. I hope I'm saying his name correctly. I'm a little stuffy, so if it comes off lost in translation, I apologize to Frank and anyone else who knows him. I wanted to I know that as we kind of get things started here, one of the things that's really on folks' mind is sort of the fully autonomous, lethal autonomous weapon system. The ones that are fire, find, and forget, using some of the GG and some of the language that they have cited from Libya and also in Ukraine. And initially, we're wondering what your thoughts were on sort of global deployment and acceleration towards use of these systems, especially when you have disparate forces. In one case, you've got a very small military force facing a very large force, and wonder what your kind of initial thoughts on that might be.
Yeah, and that's actually what Frank and I talked about, right? It's the idea that in the US, we're really operating kind of still in peacetime, right? And so in peacetime, what we always want to do is test to the best of our ability, right? In the most rigorous way, within some reasonable time and money constraints, of course, but we really, we have a responsibility as a democratic nation, right? To not field anything that's going to be a liability, that's going to potentially be less than, optimal in a variety of ways. We need to be able to trust these systems. So there is a cost to that, both a financial cost, but also a tremendous time cost. And that time comes from two places. One, the science of test is not as mature for AI-enabled systems, right? So testing is not, up until recently anyway, has not been as attractive to developers as just building systems, right? We're building them a lot faster than we can test them. Testing requires science, it requires a tremendous amount of infrastructure, right? Consider just how many adversarial representations we might need, or the size of models simulations, or the test tools that are required to take all of these measurements. So all of this takes time to catch up. And the other suck, if you will, is once we find errors, somebody has to fix them, right? And that's not, that time is often ascribed to the testers. That's not actually our fault, right? But once we find errors, it does take a lot of time to fix these systems, and they do tend to be fairly brittle. So there's a lot of work to be done in that area. There are ways to mitigate some of that, like do a lot of testing early and often, and then you're giving yourself a lot more time to diagnose and localize issues and fix them. But nevertheless, it's very much a process. And so while we're at peacetime, we're always going to be super rigorous with that process. What we're seeing in Ukraine, though, is hackers sitting in the trenches with the warfighter, right? And instead of taking years like we are, taking days to field something, right? Because they are not in peacetime. And so that was kind of what Frank and I talked about a little bit is, what would happen if a conflict were started and we weren't ready, right? And that's thankfully not my decision, but somebody has to make a decision what level of risk they're willing to take depending on the situation. And our military leaders are trained in operating in exactly that kind of uncertainty, right? Making decisions in highly uncertain situations while maintaining our democratic ideals and following our laws. So I'm grateful that it's not my decision and that we have the kind of people that we do who do make those decisions and are trained to do so.
No, and thank you for that. And I think that kind of answers a little bit what Mark Meyer was asking. And if I understand the question correctly, it's kind of that line between kind of the guardrails that are needed for an AI tool to not kind of go in its own direction. We're seeing a lot of reporting right now that seems to indicate that AI can even self-improve. It can learn from itself. It can write its own code. And I think that's probably invited some angst into the situation. And I also was very appreciative of your comments. This is a subject near and dear to my heart of kind of workforce development and ensuring that we've got kind of that competent operator, not just senior leader, but kind of all the way through the spectrum. And so forth.
Yeah,
so
I mean, I think the comments about self-improving AI, I think that's very optimistic at this point. What I worry about more is the idea that right now we're relying on humans to catch a lot of the AI errors. And so I do worry about overloading the humans or relying on the humans too much in that role. And so I worry about what might happen when we get to superhuman decision-making speed. When the humans are no longer there to kind of provide that safety net, because the goodness of our AI then has to improve very substantially if we're no longer relying on humans to catch those errors.
And that brings up kind of an interesting question. I know it's sort of in the scholarship right now, and I know that you're tracking this probably very carefully. Is if you do have that super intelligence, are we even if it's 10% or 1% smarter than even our smartest, our best and brightest, are we really going to be able to understand it and detect it? And so I would be interested in your thoughts, perhaps on how you see that maybe unfolding.
I'm not sure I'm really ready to answer that because I don't know how intelligence is defined in that context. In many in a very large sense, we already don't understand what these models do and how they do it, right? I mean, you look at the DARPA's Explainable AI initiative, that was 5 years of DARPA smart people working on it, who ultimately concluded that explainability is really hard, and that we don't know what makes a good explanation, and that we don't know how to make a machine explain itself to a human. But they did conclude that trying to make these systems more explainable ultimately leads to more robust systems. So I thought that was a really interesting takeaway point. So that's really not, I guess, where my mind goes. That's not what I worry about. I worry about robustness of our systems right now. I worry about how brittle our systems are because we're building them based on open source software. And I worry about being able to test them thoroughly and having that kind of infrastructure and having that kind of knowledge and metrics and frankly motivation to test them thoroughly. Certainly generative AI is kind of, you mentioned, it's introducing some really interesting, it's throwing some wrenches into the way that we think about things. So we're trying to figure out now, how do we test that and where is it useful and how might a warfighter use it? So all of these really great questions, really great time to be in the testing space. Definitely wish we were maybe under a little bit less pressure, from our near peer competitors, to get this figured out really fast.
Indeed. And we had one question. I'm not sure if people are waiting to stay over time. We are at time right now, so I want to ensure that we're respecting everyone's schedule. Dr. Jane, if you're interested in answering perhaps one more question from Matt
Yeah,
Nguyen.
let's do it.
Yeah, as I see it in here today, he thanks you for your presentation, of course. Very, very interesting and very, very cool. He asks, whether or not there's been a lot of decision or a lot of effort placed in the decision space for comparing or contrasting new AI policy with, say, for example, the Vietnam era, radar warning receivers, autonomous systems, and so forth.
Yeah, the most comparisons that I've seen have actually been with the nuclear industry. And the comparison that just kills me is that when it came to nuclear weapons, we dropped it first and thought about policy second, right? And that's really something that we're trying to avoid in this case, but it does highlight why it's so difficult, right? Is because we haven't really deployed it. We don't really understand all of the consequences, right? But we're trying to prescribe policy. And at the same time, we're also battling this. We don't want to stifle industry innovation. We don't want to stifle DoD innovation. So we're trying to be not too prescriptive with our policy, prescriptive enough to be responsible. And so it's a very delicate balance to be struck there. There's also some comparisons I've seen with like radar gunnery, as you mentioned, because of just the way that, how people are willing to adopt technology and whether that affects, how they do in the next battle. And then there are a lot of parallels, also with the nuclear technology in that, it's kind of, in many cases cannot be thoroughly tested, right? But nevertheless, we try to build that assurance case. So that's probably the closest that I could come up with in terms of other industries that we can compare ourselves to.
Well, that's perfect. Well, thank you so much, Jane. This has been wonderful. I do know we're at time, and it's always a wonderful thing when it's so interesting of a topic that people want to keep asking questions for hours. So, well, thank you so much. It's again great to see you. I hope you had a wonderful Thanksgiving, and we will look forward to future opportunities for collaboration. I hope you have a great rest of your week.
Sounds great. Thank you. Thanks, everyone.